Hello, everyone. Happy Friday. It is Friday the 13th. We're going to briefly today start talking about Chapter 5.3, which involves atomic emission spectra and the quantum mechanical model. So this whole unit's really been about the quantum mechanical model, but now we're going to apply a little bit farther than just electron configurations and quantum numbers and all that stuff that we've done so far. So we're going to be in 5.3, so you need to, other than just watching this video to get credit, you need to fill out your notes as well, okay? So a couple of the learning objectives that we're going to need for this unit or for this section would be to explain what causes the atomic emission spectra and explain how the frequencies of emitted light are related to changes in the electron energies. So we're going to talk about wavelength, we're going to talk about frequency, we're going to talk about energy, and we're going to relate them all together. Now, we will not get that far probably in this video. We're just going to cover about probably the first third to maybe half, but probably first third of this section, and we will talk about it together on Monday. Okay, so we need to understand what atomic emission spectra is. And if you go back here, it's the light that you see, all right? It is the light that you see no matter if it's visible light or if it's another form of light. And we have more than just the visible light that you see. And we will talk about that in just a moment. So we're going to talk about first the nature of light. So the first thing we need to mention is wavelength. And we have a symbol that we use for wavelength, which is represented by the Greek letter lambda down here. Okay, so we need to know what wavelength is. It is the distance between the top of each wave, and we call that a crest. Okay, so the top of a wave is called a crest. The bottom of a wave is called a trough, and the distance between the crest is the wavelength, and then the distance between the height of the wave from zero right here to the crest is called the amplitude. And these are words you probably heard before, wavelength and amplitude, and maybe frequency as well. It may have been if you thought about music, because that's involved in that as well. But in actual chemistry, when we talk about wavelength and frequency, we have to relate it back to the speed of light and to energy, because those are all properties of light. So we will get there. So that's wavelength and that's amplitude. Okay, so it's a little bit of math in this section, a little bit of formulas we're going to have to use. So the next property of light that we need to talk about is frequency, and that is represented by V, and that is the Greek letter nu there. And that is the number of wave cycles to pass a given point per unit time. So how many, and usually it's in hertz, which is what you see underneath this. It's inverse second is what hertz is. But that is the number of times a wave actually goes through in a certain amount of time. And we usually talk about that in terms of hertz. So the SI unit for cycles per second is called hertz. Okay. And hertz is a inverse second. So, if it takes you 30 seconds to do something, hertz would be 1 over s, or s to the negative first. Okay, it's a reverse second or inverse second there. Okay, so moving on, looking here, you have this formula that you need to know, and well, you'll have it, but you need to be able to apply it, which is C equals lambda times nu, or in other words, the speed of light right here, which is for C, that's a constant, and that equals the wavelength times the frequency. Now, when we do the math for these problems, the speed of light does not change. It is what's in yellow underneath this, 2.998 times 10 to the 8th meters per second. We could use different, I guess, units. I mean, we could convert that to feet per inches or miles per yard or miles, not feet per inches, feet per minute or miles per hour or whatever. But we want to keep it generally in meters per second, because if we look back at what we had, wavelength right here, wavelength's going to be measured in a distance. Wavelength, its length. It's going to be measured usually in nanometers, but we can convert that to meters. And hertz is an inverse second. Okay, so it's 1 over s, which is what this is represented by. So wavelength, if it's meters right here, and frequency, if it's 1 over s, if you multiply m times 1 over s, you get m over s, which is what the units are for the speed of light. Okay, so what you need to know from all that is that this does not change. This number stays the same always, as we talk about this stuff in a vacuum. Okay, so this is an inversely proportional relationship because when one thing goes up, the other one goes down. So when you increase the frequency of something, the wavelength is going to decrease, and vice versa. If you increase the wavelength, the frequency is going to go down. So um, we have the whole electromagnetic radiation spectrum that shows that, and we'll get to that in just a moment. So this is an inversely proportional relationship that you must know. So the frequency of something, if you look down here, low frequency here, you know, the number of waves that pass a given cycle is not as much here as it is here. You know, it's happening more frequently here in this certain cycle. So from here to here is a cycle, you have one full one, and then you have two right here. Okay, right? You see that where my mouse is? You start here, to get back to there, that's 1, 2. So in this distance right here, it happens twice. But likewise, for here, it happens 1, 2. So if I start here, let me start over. 1, 2, 3, 4. It happens 4 times. Okay, there. So this has a higher frequency, and the wavelength. If you look right there, the wavelength is shorter. It's a shorter distance than right here. So you can't increase the frequency without decreasing the wavelength, and you can't decrease the frequency without increasing the wavelength. It does not happen. It has to happen that way. So we combine all this to talk about the electromagnetic radiation spectrum. Now, these right here that you read are the different parts of the electromagnetic radiation spectrum. So we go all the way from radio waves to gamma rays. Now, we usually, a lot of this we don't see, right? We only see the visible light. That is what we see. The colors that we see is visible light. Now you've probably heard of most of these. I'm sure you've heard of radio waves. I'm sure you've heard of microwaves, probably infrared, also UV, X-rays, and probably gamma. Most of these I would assume that you've heard of. Now all of these waves travel in a vacuum, right? No pressure, at a speed of 2.998 times 10 to the 8th meters per second, which is the same as this. Okay, it's the speed of light, meaning all of these travel the same speed. All of these. So if you were asked what speed do the radio waves travel, it's the speed of light. Okay, because these are all light. Because light is dual natured, and I think that's coming up. Light exists as a particle and a wave. So when sunlight passes through a prism, the different wavelengths separate into a spectrum of colors. You've probably seen that. Okay, so going back to here, of all these, that's probably most applicable. Visible light is definitely the most applicable one here for you because it's the one you see the most often. But in the order that we're going to go and in class or distance, we are going to label this, and hopefully you can color it as well. That's going to be the point of this. The red light has the longest wavelength and it has the lowest frequency. So if you think about the rainbow, you have Roy G. Biv, red, orange, yellow, blue, red, orange, yellow, green, blue, indigo, violet. I knew I was forgetting one. Violet would have the shortest wavelength and the highest frequency. So a reason or a way to remember that is that I went over too far. If you look here, visible light. Before visible light is infrared. Okay, so that would mean after infrared comes visible light, but the first light that comes is red. Red, first color that comes is red because it's next to infrared, which is why it's called infrared. And then the closest one to UV in terms of color for the visible light is violet. That's why it's called ultraviolet. After violet is ultraviolet. So the most dangerous visible light that we have is violet, and the least dangerous one we have is red. Okay. So what would have the shortest wavelength and the highest frequency? That is violet. That's on the opposite end. Okay. So this is what it looks like. So your range of a wavelength in the visible light spectrum is from 700 to 400. Okay. So that's a range of 300 nanometers, not meters, nanometers. Very, very, very small unit. Okay. So radio waves have the highest frequency, which is why in your car you can hear the radio from a good distance away from wherever it's playing at. And there are stronger radio waves than others, but that go farther at least. But you can hear those pretty far away, right? The next will come radar, but that's not one of the seven you need to know. After that is microwaves. Right? Microwaves are useful in cooking or heating up food. If microwaves were very, very dangerous, then it would be bad to actually have them in our homes and things like that. But they're not that dangerous. So as you can see here, as you go left to right in terms of increasing frequency there, the farther you go right, the higher frequency is and the more dangerous it is because that has a higher energy. Okay, and we'll get to that on Monday or Tuesday. So gamma rays would be the most dangerous. Gamma rays cause radiation. X-rays, every time you get an X-ray, you have to put something that either has lead, or it's usually lead, or some other heavy metal on you to prevent those rays from going through you in places they don't need to, right? If you get your teeth X-rayed or whatever, you always get. I mean, every time I go to the dentist and you get X-rays of your teeth, they always put this lead sheet over you, so it's to prevent you from getting those in your body that you don't need them. So, and then UV, that's ultraviolet. That's from sun. That's like sunburns and stuff like that. We know that's a little bit more dangerous than the red. And I skipped infrared, but that's the like the night vision stuff. So all of these fall into the electromagnetic spectrum here, but this is the only ones we see. I mean, you can still slightly see infrared, but really the only ones you see is visible light. Okay, so something also that I don't think you have to type or write on yours because I'm looking at it right here. But one other thing that you need to see is that when atoms absorb energy, their electrons move to higher energy levels. Okay, so that would mean from like n equals 1, that's an energy level, right? That's the principal quantum number, n equals 1 to n equals 2. To go from n equals 1 to n equals 2, you would have to absorb energy. Okay, but to go from n equals 2 to n equals 1, you would have to emit energy in the form of light because you go to a lower energy level. Okay, so we're going to do that in class a little bit next week. Okay, so if you look at this is an example of atomic emission spectra. So you have a light, you run it through a slit, very small opening, hits a prism, and then you can see all of the colors of that certain light that you're talking about. So for example, um, the elements that this would work for, such as hydrogen and helium, are the main two, but there's other ones as well. They have different atomic emission spectra. They have discrete lines that are placed here. Okay, so you need to know what atomic emission spectra is. Okay, and really all you have to write down here is it's the wavelengths of the spectral lines. So it's the wavelengths of these lines that you see. Okay, and no two elements have the same atomic emission spectrum. Okay, they have a unique atomic emission spectrum. So the last thing we're going to do here is I'm going to show you how to apply math to this. So calculating the wavelength of a certain type of light. We want to calculate the wavelength of a yellow light emitted by a sodium lamp if the frequency of the radiation is 5.09 times 10 to the 14th hertz, which is 5.09 times 10 to the 14th inverse seconds. Okay, so you can write it either way. I would know that hertz is 1 over s. Okay, so it's 1 over s. So to do this, we need to calculate wavelength. So we need to go back and real quick, this is the formula we need. C equals lambda times v. So speed of light equals wavelength times frequency. Okay, so we know the frequency. They gave us the frequency. The frequency of this yellow light is 5.09 times 10 to the 14 hertz. We have that, okay? We also know the speed of light. That is a constant. That is not changing, okay? So we know C and we know V. So if you look up here, we know this and we know this. So we have to figure out what the wavelength is. So that's what we don't know. So to do that, you rearrange this equation, right? Like you would anything else in any math class. You had to get wavelength by itself. So when we do that here, we have C over V. So you take the amount, the speed of light, and then you take the frequency down here and you divide these two, okay? So you just put it in the calculator and you're going to get 5.89 times 10 to the negative 7 meters, which is good because meters is a unit for wavelength. That's what we need. The S right here, these are going to cancel out because you have an S times 1 over. We have 1 over, well, at the top you have 1 over S, and the bottom you have 1 over S, and it ends up flipping around. I'm going to show you what that is in person or in another video when we get there. But that's what it cancels out essentially. And you're left with 5.89 times 10 to the 7th meters. Okay. So 5.89 times 10 to the 7th meters, what you will see is that is 589 nanometers. Remember that, 589 nanometers. Okay. So the wavelength of a yellow light, according to this question, was 589 nanometers. So let's go back and look here. Okay. That makes sense because visible light should be between 700 and 400 nanometers. Okay. 589, the middle between these two, the range is 300. So divide 300 by 2 is 150. So the middle right here would be 550. 589 would be a little bit more than 550, and that's closer to this end, and that's where it would be at, okay, around here, which makes sense because it's yellow light. It's going to have a wavelength that's around that amount.